Hello, welcome to section 11.2 to 11.3 for astronomy class. Let's go ahead and get to it. So 11.1, introducing us. 11.1 said stars form from the gravitational collapse of immense clouds of interstellar gas and dust. So let's go ahead and start with 11.2. Most stars shine throughout their lives by converting hydrogen into helium through nuclear fusion. We learned how to do that. Not how to do that. We learned about that a couple chapters ago when we were specifically looking at our sun. We saw the proton-proton chain, how hydrogen turns into helium. Remember, for every 4 hydrogens we had, we ended up with 1 helium. And that's all the process of nuclear fusion is. I say that's all as if it's something super simple, kind of easy to understand, but in reality, it's not. And in reality, it's super crazy complicated. So as long as smaller atoms are combining to make heavier atoms, nuclear fusion is happening. Stars spend the majority of their life cycles consuming the hydrogen and forging heavier elements, releasing energy in the process. So our star consumes hydrogen and makes helium, which is a heavier element. And we talked about in the proton-proton chain, that does release a bunch of energy. That's how the energy gets into the sun. That's how we get energy from the sun as well. It's all down in the core of the sun. So then a question like this that says, where does the increasing amount of helium come from inside the core of a star? Well, it comes from them being made, right? Nuclear fusion is making them. It was a bunch of hydrogen squeezing, becoming helium. So there's more and more helium inside of a star because more and more hydrogen is being converted into helium. Just so you guys know, the total time that a star will spend fusing hydrogen into helium is called its main sequence lifetime. So for our sun's been burning for 4.5 billion years, and it's on, it probably has 12 billion years worth of fuel in it, so it still has quite a bit to go. But what normally happens when stars are forming is that they form in clusters. Remember we talked about either a supernova squishing a bunch of gas, or 2 gas clouds kind of mixing together. And if 2 gas clouds mix together from the same interstellar cloud, then all stars will have similar chronological age and initial chemical composition. So they all kind of have the same thing going on because they're from the same clouds. Now, that doesn't mean that they all enter the main sequence at the same time. Because remember that graph from 11.1, some of them start at different times. Remember, the larger the mass of the protostar, the quicker it enters the main sequence. The small ones take quite a bit of time to even enter the main sequence, whereas the large ones, since they have so much mass, their cores can get hot really fast and they can enter the main sequence first. So it's a little strange. They have a similar chronological age, but they haven't been in the main sequence for the same amount of time. They were formed at the same time, but they did not become a regular star at the same time. And initially they had the same chemical composition, but as we will learn, different masses can produce different things going on. So here is an amazing picture. I think it looks so cool. We're going to zoom in on this nebula right here, this part of the nebula, which kind of looks like a hand almost. It's pretty awesome. And here's our book picture, which is lovely, right? So this emission nebula is about 2,200 parsecs away and about 200 parsecs across. Remember, that was what, like a little more than 3 light years across, so 3 times, so at least 6,000 light years across the star cluster M16. We can see that if we zoom in right here, star formation is still taking place there. We call these like the fingers over here, that's what they say. So hot luminous stars around the edge of this zoomed in picture are emitting ultraviolet light. This makes the dark nebula evaporate, and it leaves these pillars of clouds and dust. At the tip of each of these fingers is a cocoon containing a young star, probably. Eventually, when the cocoon evaporates, we get to see the stars in between. This is some pretty crazy stuff. So if we're looking at a cluster of stars that kind of started at the same time, a star cluster's age is equal to the age of the main sequence stars at the upper end of the remaining main sequence. As a cluster ages, the main sequence is eaten away from the upper left as stars of progressively smaller mass evolve into red giants. So if we want to compare, we're going to compare these two right here. We have the Pleiades star cluster, and we have NGC 2264. This is a picture of an older cluster. There's a couple ways we can see this. First of all, if we look at the nebula, or the cluster itself, you'll notice that there's not a lot of crazy clouds all around it, right? There's still definitely some, but there's not a lot of cool clouds. Whereas if we look at this picture, there's all these crazy shapes and colors and stuff. What that kind of hints to us is that this has been around a lot longer, long enough to kind of make all those clouds go away. Whereas this has not been around long enough to make those clouds go away, right? So that's one way we think this is a newer cluster and this is an older cluster. Another way is if we map out all of the stars in this cluster to the main sequence, they pretty much line up on the main sequence. Aside from a couple of these guys kind of heading off in their own direction, most of these guys are on that line. What that means is as stars form over here, they make their way over here and they become main sequence, right? We saw that picture last section. Over here, and they make their way into the main sequence. So all of the stars have had time to enter the main sequence. Whereas here, a lot of the stars are still all the way over here. They're still making their way to the main sequence. Some of them definitely are, but a lot of them are still making their way there. They haven't even started their main sequence lifestyle yet. So that's another way we think this cluster is not nearly as old as this one. The Pleiades star cluster would be old, estimated 100 million years old, and this one estimated 2 million years. So huge difference right there. So a main sequence star of a little less than half of our sun, or larger, slowly uses up the number of atomic nuclei in its core, thanks to hydrogen fusion. Okay, it uses it up. Because of this, the core contracts slightly under the weight of all of the outer layers, which actually increases the density and temperature of the interior. And because that shrinks, everything in the center gets a lot hotter, so the fusion increases, and then the radius increases and luminosity increases. So what's happening is you have a star. As this the core contracts slightly under the weight of all the other stuff, which increases this part. And because this gets increases, thermonuclear fusion gets faster. And because thermonuclear fusion gets faster, more energy is released, and the star gets bigger. So it's this weird kind of like loop that feels like it shouldn't make sense. It's pretty interesting. So estimated, our sun is about 4.56 billion years old. 4.56 billion years ago, the interior of the sun was 75% hydrogen. That's what this line represents. Okay, but today we estimate that the center of our sun is somewhere between 25 and 50% hydrogen. And then the outer layers right here from 200,000 kilometers on is still pretty much 75% hydrogen. Okay, so it started out being the entire mass of the sun was 75% hydrogen, but now we see the inner layers are not as much. And opposite is true for the helium. Back in the beginning, 4.56 billion years ago, we see helium was 25%, but now we see there's way more helium in the interior of our sun. And that's thanks to this hydrogen fusion. All this hydrogen that was here is being used up and forming all of this helium. So it's important to note that this graph is not over time. This bottom thing is not time, it's distance. So this line is 4.56 billion years ago, and the red line is what the sun's composition is probably today. I say probably because remember, we cannot see inside of any star. We don't know what actually is happening, but we can throw a bunch of math at it and get a pretty good estimation. So as a result of that little demonstration I just did, when the sun formed, it would look like this, but as the interior kind of gets squished, it starts to heat up more and release more energy, which means the outer layers spread apart more. So since the sun's formation, the luminosity of the sun has actually gotten increased by 40%. So it's brighter now than it was when it first formed. And also the sun's about 6% larger, or it takes up at least 6% more space than it used to. And this is still due because the interior of the sun gets really hot. It pushes the outer layers farther out. Remember that thermal equilibrium and that dynamic equilibrium that we talked about in chapter 8 or something when we were talking about the sun specifically. So what happens to the size of a star if its core shrinks? We know that if the core shrinks, there's more nuclear reactions, which means the outer layers have to heat up and expand because they're getting more energy from those nuclear reactions. So as time goes on, the core shrinks, but everything else gets expanded because the core shrinking means all the nuclear reactions take place faster. Is this starting to hopefully make sense? It's like a vicious cycle. Now, if there's a star between 0.08 and 0.4 solar masses, meaning if it's 0.08 times the mass of our sun or 0.4 times the mass of our sun, these end up being the red dwarfs. Okay? The red dwarfs. And you can't really have a star less than 0.08. 0.08 is pretty much the lowest star you can have, 0.08 solar masses. They have a spectral class M, so red dwarfs have a small radius and a low temperature, hence the name, red dwarf. Remember, low temperature means red. In a red dwarf, helium does not accumulate in the core like large stars. Instead, it gets replaced since the entire star is consistently moving around in this circle. So remember, convection is these little bubbles, right? Hot air rises, cool air sinks, and it kind of makes that combo. In our sun only has it like right here, right? Our sun just does convection currents on the outside. But if the sun is small enough, the convection currents happen throughout the entirety of the sun. So as you make helium here, the helium expands, goes all the way out here, and this helium gets to go back down into the core. Our sun, the sun's helium on the surface will never make its way into the core. It can't, because the convection currents are only up here. But for a red dwarf, they definitely can. And as a result, they have ridiculously long lifetimes. Calculations indicate that it takes hundreds of billions of years for a red dwarf to convert all of its hydrogen to helium, which means that's insane. On anybody's standards, the longest prediction for or the oldest prediction our universe is like 15 billion years, right? So that means even according to that, red dwarfs have not had enough time to run out, which means you can ask the question like, what happens when red dwarfs run out of fuel? And we do not know the answer to that because that hasn't existed yet. Does that make sense? That there's none of those yet. None of those have run out because time has not existed long enough for those to run out, which is insane. So why do convection cells in the smallest of the red dwarfs result in such long lifetimes? Because they get to move fresh hydrogen from the surface into the center so that nearly all of the hydrogen in the star can be used for fuel. Our sun just uses the core hydrogen for fuel, but red dwarfs use all of its hydrogen for fuel. That moves us on to 11.3, which is a lot shorter than 11.2 or 1. So if we look at specific star clusters, we start to see how a star's mass influences how stars change over time. Let's look at these two different types of stars. We got population 1 and population 2 stars. Population 1 stars are formed from the remains of other stars, and they are metal rich. Remember, metal just means it's not hydrogen or helium. When we're in astronomy, that's what it means. Anything that's not hydrogen or helium. So population 1 stars are formed from what used to be stars, and they are metal rich, meaning they have a decent amount of metal in them. That's not to say that a large portion of them are metal, It just means compared to population 2, they have more metal. Population 2 stars, then, are first-generation stars formed early in the galaxy and are metal poor. Okay? So either way, neither one of population 1 or 2 stars have very much metal, but population 2 have so little metal, it's crazy. Population 1 just have a little bit more than that. It's a distinct enough difference for scientists to be able to pick up on. And notice population 2 are first generation. It's a little backwards, right? Population 1 stars are formed from the remains of other stars. Population 2 stars are the first generation stars. Excuse me. So here we have 2 spectral lines. Remember, each of these lines tell us something about the elements that are in the star itself. Okay? So A is a metal poor star, and B is a metal rich star. So B is metal rich. You'll notice that B has a lot more darker lines in it than star A does, right? That gives us the idea that the population 1 star has way more heavy metals in it than the population 2 star. So we assume that this star is closer to the beginning of the galaxy, and this one has probably been made out of other stars. A star was formed, exploded, and then that material formed a new star. And that's what this star is probably made out of. The relatively high concentration of elements in the Sun means that the solar nebula, from which both the Sun and planets are formed, must likewise have been metal-rich. Okay? So everything that the Sun, the planets, and even you came from the previous explosion of another star, which is insane. I'm going to read a section from the book. The concept of 2 stellar populations provides insight into our own earthly origins. Helium fusion in red giant stars can produce oxygen and carbon, the kind that's found on Earth. The reason is that Earth's carbon and oxygen atoms, including all of those in your body, actually were produced by helium fusion. These reactions occurred billions of years ago within an earlier generation of stars that died and gave up their atoms to the interstellar mediums. That's crazy. A star a long time ago exploded. In the explosion, it created carbon and oxygen, right? And then many, many years later, that carbon and oxygen got to form into the Sun, into the planets, into Earth. And if we're made from the same stuff that the Earth is made out of, then we're literally made out of dead stars from who knows how long ago. That is insane. And in fact, that's where all of these elements come from, right? Most of the universe is hydrogen and helium. There's no chunks of iron floating out there. And if they are, they came from the remnants of a star that exploded. Iron just didn't form for no reason. It formed because of all this crazy star stuff. In which population of stars is Alpha Centauri a nearby star with a size and chemical composition similar to our Sun? Our Sun has a decent amount of metals, right? So if it's similar to our Sun and it has a decent amount of metals, that means it's a population 1 star. 1 meaning it has a decent amount of metals. Not that it's older, but it has a decent amount of metals. Was our Sun formed at about the same time that a universe originated? No. Our Sun is a metal-rich star, which means if all the stuff that we're talking about holds true, then our star had to have been made from the remnants of a previously existing star, which is crazy to even think about. The most important characteristic, then, in determining a star's main sequence lifetime is its mass. The more massive a star, the more rapidly it gets to go through all the phases of its life. And we think like things like red dwarfs end their lives eventually as just a ball of helium floating out there, but none of them have burnt out yet because remember, they'll take like hundreds of billions of years, so we have no idea what's going to happen. Like, no idea. Here's like a little chart example, and you will have an assignment based off of this that will be posted soon. Spectral class goes like that. We see the masses when compared to the Sun, surface temperatures, luminosity compared to the Sun, And the main sequence lifetime, you do 4 times 10 to the 6, or 15 times 10 to the 6, or 700,000 times 10 to the 6, which gets gigantic numbers over there. So a question like this, how come the O and B stars have the most fuel? Why do they have the shortest lifetimes? Well, if they have the most fuel, they compress the core, right? They have the most stuff, so they smush the core, which makes it super hot and makes it more dense, which means it burns through the fuel faster. Since it burns through the fuel faster, its main sequence lifestyle is shorter. And that's about it for this week, guys. So hopefully we're getting used to this whole crazy online stuff, because it's going to be like this for a while. Make sure to keep up on your homework, and if you have any questions, remember you can always see me on the Tuesday, Thursday meeting times. That's about it.